Hello, everyone, and welcome to today's InfluxDB IOx Tech Talks. My name is Caitlin Croft, and I'm happy to see you all here. If you've been on any of our webinars, you know that we like to give everyone else just a couple of minutes to join, but I love how many of you have already joined at the top of the hour. Before we get started, just wanted to go over a few friendly reminders. This session is being recorded and will be made available later today on YouTube, and the slides will be made available as well, since I know a lot of you like to review that and, of course, check out the presentation again. So later today, it'll be available for replay. We have lots of different virtual events for you guys. We love sharing stories of how community members are using our product and just getting as much information out there as possible. So be sure to check out our website if you're interested in attending any of our other events. We have a InfluxDB cloud product update coming up, as well as Flux intro to Flux training and lots of other webinars. And we have these InfluxDB IOx Tech Talks every month, so we definitely like to see you guys come back, and it's always fun seeing familiar names pop up on the screen. Once again, other friendly reminders, we of course have our community Slack workspace, and there is a IOx channel, so you can definitely go there and ask more questions and help each other out. I know Paul and the rest of the IOx team are in there answering your questions as they come in. We're really excited to have Influx Days coming up on May 18th and 19th. This is our European version. It is, of course, virtual this year, so that means it doesn't matter where you are in the world. We'd love to see you there. All the sessions, of course, from Influx Days will be recorded, and I know Paul will be giving another talk there about IOx. So if you're not tired of hearing about InfluxDB IOx, definitely come and check it out. We have lots of Influx engineers ready to go that are going to be presenting, as well as our amazing community members sharing their knowledge and sharing their tips and tricks. So it's always a lot of fun. Even though we're all virtual, we still manage to have a lot of fun and joke around over Slack and other ways. So it'll be a really fantastic conference. And as part of the conference, we also have our Flux training, which we've been running the Flux training now for a couple of years, and it's always super successful. So that's on May 10th and 11th. And there is a fee attached to that course, and it's just so we can make sure that there's a really great student to teacher ratio. And we also have a free telegraph training as part of Influx Days. So we hope to see you all there. All right, without further ado, I know you guys are all here to listen to Paul and the InfluxDB IOx team, not me. So welcome, everyone. Super excited to see you all here for today's InfluxDB IOx Tech Talks. And without further ado, I will hand things off to Paul.
All right. Thanks, Caitlin. Just give me a thumbs up if you can hear me.
You sound great.
Okay, great. All right. Thanks, everybody, for joining. So let me pull up my slides. One moment. And actually, while I'm doing that, I just wanted to mention that we've grown the team, the IOx team, quite a bit over the last few months, and I just wanted to kind of like introduce people, which I can do in a second. Yeah, so we've added a bunch of new team members, but just as a quick introduction, it's obviously myself, Ed, Andrew, it's kind of in order of the people who joined the team, Dom, Jacob, Luke, Marco, Raphael, Mia, and another Marco. So we're a much larger team now, so things are actually starting to move pretty quickly in terms of getting things defined and implemented and stuff like that. So even though I'm giving this talk today, and I'll be giving a talk in a month at Influx Days, my expectation is that in a month, there will be even more to talk about and more interesting things to show. So let me jump back over to Zoom to do a screen share. And all right. That look.
Looks great.
Marco, I can see you. Can you give me a thumbs up if it's good? Can you see my slides? All right, great. Cool. Okay, so today I'm going to talk about how we're envisioning one way of doing replication durability and a feature called subscriptions in IOx. And this design that I'm going to step through is basically what we're going to be doing in our own cloud setup as we dog food IOx for our own internal usage of basically monitoring a system that ingests probably at about a few million writes per second. But the overall thing about the design with replication and how you can structure things with a collection of IOx servers is that it's supposed to be very flexible to support fully federated systems. So this means operations at the edge, multiple data centers across regions, with a wide range of possibilities, from one server up to potentially thousands of servers working in different ways together. So let me just talk about some of the higher level components. You may have heard of these before, but not all of these things are required to run in the same process. They basically can be optionally configured. And in this example, we'll actually put different parts of these components into different servers. So the very first is what's called the RightBuffer. If you're looking at a single server database, this is maybe like a write ahead log. It's kind of like that, but a little bit different. But basically, it's just a place where we buffer writes in memory and offload them in basically segments of writes as they came in to object storage. And the RightBuffer is also where you can hook up subscriptions. So subscribers can pull down a stream of that data or a subset of that stream of data. The other big piece is basically the in-memory database, which is comprised of two underlying pieces. One is the mutable buffer, which is an in-memory queryable store that's designed to basically be optimized for writes. And then the other is a read buffer, which is an in-memory queryable store that's designed to be optimized for compression and query speed. And it's from this in-memory database that the persistence to Parquet files happens, which I'll cover in a second. And then lastly, there's this idea of the catalog of the database, which is the definition of what partitions we have and the summaries of the data and stuff like that. And this catalog can be used at query time to determine what data needs to be queried. So this is basically the larger diagram. We're going to layer these components onto this diagram. Now, each of the blue boxes represents a separate IOx process running in a different container. There's another detail in this diagram that wasn't mentioned before, which is the concept of sharding. Sharding exists only to horizontally scale writes. That's the only purpose it has. The shard information isn't persisted and doesn't change how data is organized in the object store, other than the fact that it partitions writes across various servers, which is reflected in the object store. So the idea is that partitions exist to split data up for the purposes of breaking it up at query time. So for example, we partition data by hour. When a query comes in, we can see that we only need to hit these partitions to answer the query. So basically, partitions exist to help us manage the data lifecycle from memory out to object storage, and shards are there to split up the workload of ingest across many servers. Now let's look at the routing layer, the top part of this diagram. So the routing layer, its responsibility in this is basically, a request comes in, either a write of line protocol, or we'll have a gRPC protobuf API soon. So basically we parse that request of line protocol, and break it up into flat buffers. We split that into shards, and then for each shard, we split that into partitions, and basically you have multiple partitions contained within an entry. So basically, we break up all this line protocol into these different shards, and one entry goes out to each shard. In the simplest configuration, obviously, you don't shard beyond just having a shard and all this in one server. But in our case, we're using the routing layer to do a few things like take the work of parsing the line protocol and figuring out how to split it out into shards, and also generating the partition keys. The nice part about this routing layer is that it can be independently scaled, and it's basically like a stateless routing layer. So it's easy to scale horizontally. So now we'll get into basically the shard layer. So when the router sends an entry to the shard, it can be to one of multiple destinations. It could be different destination types. That shard could be represented by a single server. It could be multiple servers that store that shard. It could be the RightBuffer that you're writing into, or it could be just the in-memory database that you're writing into, right? The point is you're writing to a remote IOx server, and that IOx server could be filling the role of a RightBuffer or the role of the in-memory database. So the target can be one of a group of servers, which means basically you have a group of servers for a shard, and you want to make a request to just one of them to make sure it happens. And if that fails, you go down the list and make it to the next one. Or you can say that you want that request to be routed to multiple servers. So let's look at the RightBuffer. So we've got past the routing layer. Now we're down into the RightBuffer. Like I said, this is where we handle subscriptions. The data, when a request comes in, we just buffer that data, and separately we send it out to subscribers outside of that request response loop. But the RightBuffer can also do persistence. We persist that buffer to object storage periodically. And it's how we handle replication. So we'll work through basically an example of how all that looks, like the request cycle. So first we have the router, a write request comes in, it sends it to one, and in this case, we're just looking at a single shard, right? So the idea is we have 3 RightBuffer servers for one shard. So it's going to send it to RightBuffer 1. RightBuffer 1, when it receives the request, assigns a clock value to that entry and a writer ID. So the clock value is basically going to be a lamp or clock, which we also pin to the actual system clock. We use the system clock to advance it. But basically what this means is it's a U64 that's guaranteed never to go backwards, right? So the combination of the clock value and the writer ID uniquely identifies that entry within a database. So once it's done that, it makes a request to its peers to send that entry to them. And note here in this diagram that the request from the routing layer to RightBuffer 1 is actually still open while RightBuffer 1 is trying to replicate this entry to its peers. So next we'll say that RightBuffer 2 receives it and it responds back to RightBuffer 1 that it has it. And in that response, it says what its clock value is. So, and it also updates its own internal logical clock to either the max of its clock or the max of the clock value that it just received from RightBuffer 1. So buffer 1, upon receiving that response from RightBuffer 2, updates its clock value to the max of either what it had before or what it saw from RightBuffer 2. So basically what we're doing is we're advancing the clock values of the RightBuffer servers as they replicate to each other. So after this, in our example, RightBuffer 1 has only received a response from RightBuffer 2, but it knows at this point that it plus RightBuffer 2 have a copy of the data. So it has a quorum. It sends a response back to the routing layer that says, we've got it. And then the routing layer responds to the client. Now, The one thing I should say is if you have many shards and the write is broken up across multiple shards, the routing layer will not respond successfully until each of those shards has accepted the write. That means a quorum in each shard has accepted the write. So separately, RightBuffer 1 is still trying to replicate that write to buffer 3, and it's just going to continue to retry that. So then the question is, like, what happens if one of these servers fails, or if like they become inconsistent somehow? Well, there'll be an API on the RightBuffer servers where an external operator can make a request to have those servers do consistency checks with each other. So they can ask their peers for any data that they have missing in their buffer. And basically what they do at that point is once they've synced that, they have a high water mark, which is basically whatever the logical clock value is that they've agreed on. And basically when you do those consistency checks, you only have to check the entries that came in since the last high water mark. So however frequently you want to do those checks, but they're decoupled from the process of actually receiving the writes into the system. So the other thing the RightBuffer layer, as I mentioned, is it can do persistence to object storage. And again, this is just optional. The entire RightBuffer could just be entirely in memory and you could skip the persistence. But if it is persisting, it collects those entries into what we call segments. And those segments are individual files that get put off into object storage. And when those segments are captured can be based on either time, a period of time that has gone by since it got opened, or the size of the segment, or it can be done explicitly through an API call. And again, like each one of these RightBuffer servers can be configured to persist or not persist. So if you wanted, you could have a situation where you only have one of them persisting at a time, right? Because once you get it off to object storage, you've got multiple copies of it. So you could have a situation where you've decided you're just going to make one of these RightBuffer servers the primary that is persisting this data. So separately, the thing that the RightBuffers deal with is subscriptions. So subscriptions are a way for downstream subscribers, obviously, like the InMemory database or monitoring learning systems or other systems to pull back a stream of this data. Now they can subscribe to everything that for a given database. This is on a per database level. They can subscribe to everything or a specific table or a regex that matches against a table name and or a predicate, right? So a predicate would be like just a column. You say like, I want to subscribe to the stream of data from this database, but only where the host equals foo, right? And these subscriptions work both in a push basis so that the RightBuffer can push the data out to the downstream subscribers, or they can work on a pull basis. So the downstream subscribers will hit the API of the RightBuffer and ask for it. And then the last piece is they could subscribe to this data by not touching the RightBuffer server at all. They could just pull object storage for new segment files as they appear, which is kind of nice because then you can get a kind of like a replicated system that's completely decoupled from your production like ingest path. So for the subscribers, in our case, we have a bunch of in-memory databases. So this allows us to trivially scale the query tier. If we need for a given shard more query capability, we can just spin up new query servers that subscribe to that data, and they can pull that data both from object storage and the more recent data from the buffer. So the goal with the in-memory database is obviously to answer queries, but also to gather larger blocks of data that we can persist to object storage as Parquet files. And the goal there obviously is like the Parquet files are going to give us better compression, and ideally it'll make it faster for us to materialize that data in memory to query against it, or we can pull the Parquet files to the local disk and query against them directly without actually reading the entire thing into memory. And we can do that on a table by table basis. So now we're back to the entire picture. So what we have at this point is we have an ingest path that's isolated from the query path. We can scale ingest separately from query, and we can bring up new query servers by pulling all the data that we need from object storage, except the absolute most recent stuff, which we'll just pull from the memory of the RightBuffer. So we're in the process of building all these different pieces right now. They is getting sent down, encoded as flat buffers so that we can avoid serialization and deserialization costs. And that is all I have for today. It's a quick one today. So we have time for Q&A if people have questions.
Perfect. Thank you, Paul. So if anyone has any questions for Paul or the entire IOx Tech team, please feel free to post them in the Q&A, or even if you want to raise your hand, I'm happy to unmute you.
Anybody?
Bill?
You can use, I think you can use the chat in Zoom, or there's the Q&A feature. There's also the IOx channel in our community Slack as well. No.
How does network downtime?
You share the underlying tech. So the IOx code is all open source. It's up on GitHub right now. It's written in Rust. We're using obviously Apache Arrow pretty extensively. The Parquet stuff is from Arrow. We're using the query engine is actually called Data Fusion. So that's written in Rust and part of the Apache Arrow project, but we also have our own query executor and in-memory format that's optimized for, like I said, compression and query speed. So yeah, it's basically a mix of a bunch of different stuff, but the overall design goal in terms of like, what are the different services that you need to operate this system is obviously you have to run IOx servers. We're going to be running it within Kubernetes. And obviously you need an object store that's available. And then separately, we have another piece of software that we're writing called Conductor, which is for our own use in our cloud offering, which basically organizes all the operations of all this and configures the individual IOx servers and makes sure it does all the consistency checks and all that other stuff. So I hope that answers your question. Okay, so I see there are 3 in the Q&A really quick. Okay, so the question is, how does network downtime play with page 14 of the slides? So let me pull up page 14 really quick. Okay, so from current slide. And let me just do a share really quick so other people can see this so we can talk about it. Where are you? There. Okay. So network downtime. So essentially, if the RightBuffer is unable to reach object storage, it will be unable to persist. Now, I will say that the object storage abstraction that IOx uses can use S3, Google Storage, Azure, or any one of the compatible ones, but it can also use a local disk. So writing to object storage could end up being just a call to the local disk. But if the object store is unavailable, whether that's your local disk or whether that's the network addressable object store, it will not be able to persist. Now, there are configuration settings in IOx that you can set to say what happens when the memory of the RightBuffer fills up, right? You can reject writes, you can throw new writes on the ground, you can throw old data on the ground and instead opt to keep a flow of incoming data. So it's kind of dependent, but there is definitely part of the design, the assumption that you have an object store available and the availability of the individual servers that have to persist data is going to be limited by whatever the availability of your object store is. Can you throw some light on indexes? So generally speaking, we don't have indexing beyond the partitioning data. So as a user, you can define how you want to partition data. Like I said, in our case, we're going to be partitioning data like by the hour or by 4-hour blocks. So what that means is the catalog keeps a record of like what these big blocks of data are, so that when a query comes in, it can look at it and determine which of those big blocks of data have to be touched. And essentially, like beyond that, once you get down to there, the idea is that brute forcing the query will be fast enough to give you quick answers. So it all depends, but again, it depends on what your query pattern is, right? If you're querying across all time, that's good, and you have a lot of data for all time, it's going to be a very expensive query. Now, I guess I will say, like, because of the fact that the subscribers are decoupled from the other stuff, like if you wanted to, there's nothing to stop you from building secondary indexes outside of the system. And indeed, you could have IOx servers that are downstream subscribers that themselves partition the data in different ways, right? So one could partition it based on hour, whereas another could partition it based on some other criteria that better matches with the way you're going to query the data. But then you kind of have to sort out which IOx servers do you hit based on what query you're doing. So what's the difference in the memory layout between the two in-memory formats, mutable versus query optimized? So this is actually changing a lot right now as we speak. The mutable buffer previously was essentially like you'd have a partition, and within a partition you have chunks of data. Within that you have a table. Each table has basically a vector for each column, and data as it comes in just gets appended to that vector. And separately, there's like a dictionary that the mutable buffer keeps. But again, that's kind of being changed as we speak. So the other format that I think is more interesting is the RightBuffer format. And actually, I would say Ed gave a talk on this, I think it was February's Tech Talk, which is up on YouTube, where he digs into the details of what the RightBuffer format looks like. But it's very different. It has different encoding schemes based on the data to basically optimize, like I said, compression and query. So next question is, I understand this new generation will be compatible with the version 2 of the software. Will there be any differences in query scripting languages such as Flux? So the plan is that IOx will be a backend, an optional backend to an upcoming point release of InfluxDB 2.x, right? So you'll be able to use that. And what that means is you'll be able to query it via InfluxQL. You'll be able to query it via Flux. IOx natively supports SQL. Specifically, it's the Postgres flavor or dialect of SQL. So if you're using IOx, you'll be able to query it directly using Postgres SQL. I have a separate kind of evil plan, which is to embed Dino, which is a Rust and C++ based JavaScript engine, into IOx, so that you could use potentially JavaScript or TypeScript paired with SQL queries to do query processing and in server like scripting. Let's see, will IOx be the new version of InfluxDB, or will it be a different product in parallel to the actual? So within our cloud offering, it will just be a new service that represents part of the cloud offering. So how it will look is essentially like it will replace the storage service that we have, and then new features will become available in cloud based on functionality that gets added to IOx. So essentially it will be a seamless transition. Like if you're a Cloud 2 customer, it will be a seamless transition from the current storage system it uses to what IOx is. In the open source, we're going to be creating builds of IOx independently of builds of InfluxDB. So as a user, it'll be possible to use IOx on its own, but the plan, like I said, is to have it so that if you're using InfluxDB2, you can use IOx as the backend. And what that will look like is you'll have a process that's running InfluxDB2, and you'll have a separate process that runs IOx. So it's kind of like a different product in parallel, but the goal is that it enhances and complements InfluxDB2.x. All right. Do Parquet files serve as a convenient way to store info on disk and restore it to the database as a columnar-based file format? Yes. Yeah, the goal with the Parquet files was, one, we wanted a format that was more common with other systems. We wanted it to be easier to share the data with other systems, and most data warehouse projects or big data processing systems are able to work with Parquet data directly. So that was one. And then the other is, based on, because we have object storage as the persistence layer and Parquet files, like backup and restore becomes like a totally different thing than what it looks like right now, right? Because the backup is, you already have the files in object store, and, depending on the object store, you can enable a feature there to make multiple copies of them or whatever. To restore, you can bring up an IOX server and just tell it where to load the data from object store. And it can do that either all of it, or it can do it opportunistically based on the queries that are coming in and all that kind of stuff. So that was absolutely a goal. Are there any machine learning features introduced with the new system for developers? No. The goal there actually is what I hope is that the subscriptions functionality, well, two things actually. Subscriptions will make it easier for people who are writing machine learning code to receive data as it arrives to make predictions. But the bigger thing, I think, is that because we have large blocks of data persisted as Parquet files in object store, our goal with IOX is to have a native API for doing bulk data load and bulk data access. So this is the thing that's really tricky if you're storing data in InfluxDB right now and you want to build machine learning stuff around it, is to train a model, you generally have to load this massive quantity of data. And the thing is, like, the way data is stored and indexed in InfluxDB right now is it's not fast and good at that. Like, you're better off storing your bulk data in an object store, training the model separately, and then using InfluxDB for ingesting data to make predictions and outputting your predictions. So I think with IOX and with the bulk data capabilities, it'll be easier to train a machine learning model. And I guess one other thing that's actually important in this as well is that Apache Arrow Flight is an API that we already have built into IOX. So basically you can send a SQL query and you can get data back via Flight. And if you're writing machine learning code in Python or R, they already have libraries for first-class libraries for connecting to a service that implements Flight and basically sending a query and getting the data back and instantly loading it as a data frame. And it's super, super fast compared to going through like JDBC or any of this other kind of stuff. So we support Arrow Flight as like a first-class API choice because of the fact that it makes it easier for data scientists and people who are doing machine learning to interact with the system and do things like train models or do analysis. Any vision for how Ballista and IOX will work together, given they're both based on the data fusion Parquet? That we actually really don't know yet. Andrew from our team would probably give a much better answer than I could. I don't know if he's around.
Yeah, I'm right here.
He is.
Yeah, so for those of you on
the,
how about now?
Hopefully that's not me.
I can hear him. You sound great, Andrew.
All right, so I'll just keep going while Paul sorts it out. So for those of you on the call who don't know, Ballista is a distributed computation. Data fusion is like a single node computation query engine, and Ballista is the multi-node is a multi-node system built on top of it that looks a lot like Apache Spark in terms of its interface. And so recently what's happened is Ballista has been donated to the Apache Arrow project. And I envision what will be happening over time is that some of the technology that was sort of prototyped and proven out in Ballista will migrate itself into Data Fusion, in particular, some details of how the scheduler works and some stuff. So there's already going to be some transfer that we'll get from Ballista just natively. I think to Paul's point of not having figured out more about Ballista is we're still evaluating a bunch of different ways to do distributed query execution within IOx itself, right? And given that Ballista effectively has a distributed query engine that runs queries across multiple different machines, I think one of the things we're going to be evaluating over the next month or so is how, if at all, we either want to use Ballista directly, take some of the ideas and use them in IOx, or do something else for IOX's own distributed compute capability. I don't know if that makes sense, but.
Cool. Thanks, Andrew. How will storing data in object store rather than on disk affect query times for cold data? It'll be slow. Part of the thing we want to be able to do with IOX is like a big piece of what it's supposed to provide is managing that data lifecycle of data ingest to query processing, out to object store, and then back again. Now, any query that has to go to object store to get the data is obviously going to be slower. It's not going to have to get everything. Like our goal will be to make it so that the query planner will be able to determine the least amount of data that needs to pull back from object store to answer the query, but it's still going to be in chunks. What we may end up doing is basically use local disk as a cache for data from object storage, where we can query against Parquet files directly without materializing them into the read buffer. So, but obviously, like if you're querying and you're hitting object storage, it's going to be slower than what it is in memory. Like generally, if you have a set of queries that need to be answered very, very quickly, you need to be able to fit that working set into memory. And however much memory that takes, across however many servers, like you just have to do that. Yeah. So, or again, like if you can accept a little bit slower query times, then potentially the local disk-based cache works, and even slower query times than that, you can just go fully to object store. So it seems that there's persistence with object store and with Parquet. Can you explain more the roles of each? Also difference in compression capability. I mean, the object store really just is, a disk in the sky that we can use that other people can look at. Parquet is the actual file format. So our early testing indicates that that using Parquet, the way we're organizing data within Parquet, actually lets us achieve better compression than we're currently getting with TSM and TSI. What we find, particularly in the high cardinality use cases, is that the TSI index in our current storage engine ends up being very, very big relative to all the data that you have, and Parquet doesn't have that same problem. So it's actually much more efficient, particularly for high cardinality data. So would it be possible to use both backends, for example, InfluxDB and IOX, in conjunction to store suitable data to each? In essence, would it be possible the two backends speak to each other? That's not currently in the plan. Basically, like the plan is InfluxDB will talk to IOX, so we'll be able to pull data from it. I guess it would be possible for an InfluxDB server maybe to look at its own local data and IOX data. But the way I was thinking about it was more that IOX would be a replacement for the local TSM-based storage engine. And really, like, honestly, as a goal of the IOX project, we want it to be as good for basically the set of queries that InfluxDB is currently very, very good for. We want IOx to basically be kind of on par with that. It doesn't have to be exact, but if it's close enough so that it's not that big of a deal, that's what we want. While at the same time, having IOx be dramatically better for queries that InfluxDB is currently struggling with, and that's queries across many different time series, higher cardinality, analytic kind of queries. So that's kind of like TBD, really.
There was a question in the chat. Is there API visibility?
I think that's all the questions.
Paul,
Oh,
there
sorry.
is a
What
question.
was that?
There's a question here. Is there API visibility into how full data store is in other metrics like write rates, enabling adaptive acquisition of more data store?
So everything, all those operational metrics should be accessible via either the API or via other telemetry channels like Prometheus style metrics or open tracing for tracing data and all that kind of stuff. The way we have our system organized in cloud is IOx essentially operates as kind of a data plane, like a bunch of individual servers as the data plane, and Conductor needs to be able to make decisions about how to organize those servers, how to add servers and scale up and down and all this stuff. And it can only do this if the information it needs is made available via the IOx API. So all that kind of operational information will be available through the IOx API. They'll allow you to do those kinds of things.
Perfect. Thank you everyone for joining today. We'll stay on here for another minute or two to see if anyone else has any more questions. I did throw in the registration link for next month's InfluxDB IOx Tech Talks. So it's the second Wednesday of every month. So super excited to see you there in May. And what's really exciting is the week after the IOx Tech Talks is Influx Days. So we have a lot going on next month. So we're super excited to see you all there. Michael, I see you have your hand raised, so I'm gonna allow you to talk. I'm assuming you have a question. So you should be able to unmute yourself. And if anyone else wants to talk directly with the team, I'm happy to unmute you if you'd like. Oh, sorry, Michael. There's definitely multiple Michaels on the call. See. Michael Backer, I think you had your hand raised. All right, well, it doesn't look like it. Thank you everyone for joining today's session. It will be made available later today. And thank you, Paul, and the rest of the team.
All right, thanks everybody. See you next month.